So let us see how we can use this common emitter configuration as a amplifier. So here you have the common emitter configuration. We were discussing what does the current gain. So current gain is expressed by beta, and that is equal to output current by input current. Here the output current is IC, the collector current, divided by IB. IB is the base current. So collector current by base current for a common voltage between collector and emitter. This is the meaning of writing like that. At common VCE means common voltage between collector and emitter, or constant voltage between collector and emitter. So this is the current gain. Definitely we know that the collector current is very high compared to the base current, because if the emitter current is 100%, around 95% goes as collector current and only 5% goes as the base current. So this is a large value, much greater than 1. That is why we say that there is a current gain. So the current gets increased or amplified when it is connected in the common emitter configuration. So the input current, which is IB, it will be small, but when we get the output current, which is IC, it is very large. So that is why we can use this common emitter configuration of a transistor as an amplifier. Now, it's not only the current gain, voltage is also gained. So let us see how much is the voltage gain. Voltage gain means output voltage by input voltage. So output voltage means the voltage VCE, the voltage between collector and emitter, divided by the voltage between base and emitter. So that is the voltage gain. We know that the voltage between collector and emitter means the output voltage means output current into output resistance. So output current is IC, and RL means the load resistance. In the figure it is shown as RC, but never mind, it just means the output resistance. So current by into resistance, that is the voltage. And here you have the input voltage is equal to input current by input resistance. But we know that IC by IB is equal to beta, right? The current gain. So you can write the voltage gain is equal to current gain multiplied by output resistance by input resistance. So the voltage gain is equal to current gain into output resistance divided by input resistance. Is this clear to you, voltage gain?
Yes.
Okay. Now let us see how much is the power gain. Power gain is output power by input power, right? We know that power is equal to I square R, current square into resistance. So we have written here the output current square into output resistance divided by the input current IB square into input resistance. But again, we know that IC by IB is beta. So IC square by IB square we can write as beta square into RL by RI. So beta into RL by RI is voltage gain. So you can also write the current gain as voltage gain into current gain. We know power is equal to voltage into current, right? So we can also write power gain as voltage gain into current gain. And remember, all of them are dimensionless. See the current gain, current by current, ampere by ampere. So ampere gets cancelled, no unit for current gain. Voltage gain, output voltage by input voltage, volt by volt. So no unit and no dimension here. Current gain we saw, no dimension. Resistance by resistance, ohm by ohm. So no dimension, no unit for voltage gain. Similarly, power gain, output power by input power, watt by watt. So no dimension, no unit for power gain. Voltage gain we saw here has no unit. beta, that is current gain, also has no unit. So remember, current gain doesn't have the unit ampere. It is dimensionless, unitless quantity. Similarly, voltage gain and power gain are also dimensionless, unitless quantities. Is this clear to you? The current gain, voltage gain, and power gain?
Yes.
Okay, now let me just stop sharing and I want to show you on the whiteboard a relationship between the current gain and current amplification factor. You may be asked to find or form the relation between current gain and current amplification factor, or in problems you may be given either current gain or current amplification factor, all quantities by which you can find them out, and you will be asked to find the others. So let us see what is the relation between them. We know that the current gain current gain is usually for a common emitter configuration, and it is represented by beta, and it is equal to, for common emitter, the output is collector current. So output divided by input, which is the base current. So this is current gain. And we remember that the current amplification factor, current amplification factor is for common base. We studied that it is represented by alpha. For common base, the output is collector and the input is emitter. So output current divided by input current. So these two formulas you need to remember, and let us connect these two. I will express beta in terms of alpha and alpha in terms of beta. For both of them, we need one relation, that is between the emitter current, base current, and collector current. Do you remember what is the relation? What is the relation? What is the emitter current? Emitter
IE
current.
is equal to IB plus IC.
Yes. So IE is equal to IB plus IC. Or here I can represent IB as equal to IE minus IC. So I can write here in this equation beta is equal to IC divided by, instead of IB, I am writing IE minus IC. IE minus IC. Okay. Now let me divide this expression throughout by IE, because here we need a denominator IE, right? I'm trying to express this in terms of alpha. So in the denominator I need IE. So I am dividing both the numerator and denominator, all the terms, with IE. So this is equal to IC divided by IE divided by IE divided by IE minus IC divided by IE. This is clear? So this is equal to, what is IC by IE? Alpha. Divided by IE by IE, 1. Minus IC by IE, again alpha. Alpha. So we got that beta is equal to alpha divided by 1 minus alpha. So this is an important relation which you have to memorize. Or we can use the same idea here and get an expression for alpha in terms of beta. So let us see how it is. So alpha is equal to, here I need to get in the denominator IB. So I'm going to write IE as IB plus IC. So IC divided by IE, I'm expressing as IB plus IC. Now I need to get in the denominator IB because beta have denominator IB. So I am dividing all these, the numerator and the denominator, by IB. So this is equal to IC by IB divided by IB by IB plus IC divided by IB. Is this clear? So we get here IC by IB is beta, right? So this is equal to beta divided by IB by IB is 1 plus IC by IB is again beta. So I got alpha in terms of beta and beta in terms of alpha. So if you are given one of the quantities or if you are asked to find the relation between these two, you will have to either use this way or this way. Is that clear?
Yes, teacher.
Okay, and you have to memorize one of these expressions because in numerical problems, they will give you either alpha or beta and ask you to find the other one. So let us again go and see our PowerPoint. I want to discuss one more point with you, how we can use this as a, how we can use a transistor as a switch. And for transistor as a switch, again, we will use the common emitter configuration. So when you use transistor as a switch, it's a special kind of switch. Some switches that work on light. You may have seen alarms or some lights which will glow when there is light, when there is absence of light, like that. So such special switches can be made with the help of an amplifier, a common emitter configuration. So the different types of switch are light operated switch, heat operated switch, sound operated switch. So here you can see in this figure a common emitter configuration. See, emitter is common to both base and collector. Here this is LDR, means light dependent resistance. When light falls on this resistance, the resistance is low. It will allow current to flow through. So what happens when the current is when some cell or battery is connected, when light falls, this will allow current to flow and the current flow will occur through here and the bulb will glow. Now, if there is no light falling on LDR, it will not allow current to flow through. Its resistance is very high. This means light dependent resistance. So if there is no light, current will not flow through this circuit. Instead, current will flow like this. So the bulb will not glow. Now, can you tell me how I can change the circuit in such a way that if there is no light, the bulb should glow. And if there is light, the bulb should not glow. Do you have an idea? How can I change the circuit? In the current stage, here the bulb will glow when there is light and the bulb will not glow when there is no light. Now I want to change the circuit in such a way that if there is light, the bulb should not glow. And if there is no light, the bulb should glow. Do you have any idea? Okay, I will tell you. Just switch this. Instead of LDR here, put the LDR down here and this high resistance 10 kilo ohm resistance connect here. So when light falls, the current will flow through this circuit, this loop. Current will not flow through the bulb will not glow. Now if there is no light, if the LDR was here, what happens? It will offer very high resistance. Current will not flow through this loop. The current will flow through this loop. So just by switching the LDR and the high resistance, you can change the operation of the switch. Is this clear to you? Is this
Yes.
clear? Okay. So this is how a light operated switch can be designed with the help of a transistor. Now let us see, this is the heat operated switch. For a heat operated switch, we use a thermistor. What is meant by thermistor? It is temperature dependent resistor. So here the resistance of this resistor, thermistor, depends upon the temperature. There can be two types of thermistors. One with a positive resistance coefficient, which means as the temperature increases, the resistance increases. There is another kind of thermistor where if we increase the temperature, the resistance decreases. So whatever kind of thermistor we can use here, depending upon the temperature, the resistance will vary. Suppose uh, we are using a positive, a negative temperature coefficient thermistor. Negative temperature coefficient resistor means when the temperature increases, the resistance will decrease. So when the temperature increases, what happens? The resistance will decrease. So the current will flow through this loop. And this is a relay switch. Relay switch means this is like a electromagnet. When current flow through, this will become a magnet. It will attract the switch, and the switch will on and the buzzer will go on, the alarm will ring. So if the temperature is high, the alarm will ring. Okay, and if the temperature is low, this offers high resistance, so the current will not go through this loop. Current will go through this loop, and the buzzer will not go on, the alarm will not go on. So this is another special switch designed using a transistor in the common emitter configuration. Using a thermistor, you can use it for alarm. So is the circuit clear to you?
Yes.
Yeah. Now tell me, if you are using the same thermistor and if you want the alarm to go on at low temperature, what you should do?
We should change the thermistor position.
Yes, you have to change the thermistor's position down here, and this one you can take up. Okay, that is how you can. Now here, see, here you have a sound operated switch, like a switch with a microphone. Here if you have a microphone, maybe here the microphone, also the electrical signals will be there when you speak. Okay, so it can also be used with a sound. You can switch on an alarm, or you can switch on a light if you connect a light here. So any such special switches can be made using a transistor. Is that clear how you can use transistor as a switch? As special kinds of switches. So today we learned transistor as an amplifier when it is connected in the emitter configuration, and how transistor also can act as a switch when it is connected in the common emitter configuration. Can you tell me why a transistor acts as an amplifier only if it is connected in the common emitter configuration? Why not if it is connected in the common base configuration? For common base configuration, the current amplification factor alpha is equal to IC by IE, right? Where IC is less than IE, the output current is less than the input current. So the current will not be amplified. While in a common emitter configuration, the current gain is equal to IC by IB, which means IC is much more than IB. So the output current is much more than the input current. So it can act as an amplifier only if it is in the common emitter configuration, not when it is in the common base configuration. This is a question which is usually asked for 2 marks explanation type. So you have to explain it. Now, in practice, it's not just one transistor that you use. You use a lot of transistors in common emitter configuration so that you get a high amplification. It's not a single circuit like this which is used. There will be more and more connected. So that's all I would like to discuss today.